You ever notice how the same patterns pop up in completely different places? Like seeing the same blueprint used to build both a skyscraper and a spaceship? Well, in mathematics, this happens all the time. Today, we're diving into the tool that mathematicians built to understand this blueprint. It's called category theory, and it's basically a powerful abstract language for describing structure itself. So here's the game plan. First, we're going to look at why this universal language was even needed. Then, we'll break down its fundamental building blocks. After that, we'll see how it acts like a translator between different mathematical worlds, unpack its surprisingly huge impact, and finally, we'll take a peek at the next, pretty mind-bending dimension of it all. All right, let's get started. We're on the hunt for the blueprint of math. How do you even begin to find a universal language that can describe the structure of, well, everything? So let's ask the question, what in the world do fields like topology, the study of shapes and spaces, and algebra, the study of equations, really have in common? I mean, on the surface, they seem like they're from different planets. But back in the early 20th century, mathematicians kept seeing these echoes. The same kinds of structures, the same ways of putting things together, were appearing in both fields. It was like they were hearing the same ideas spoken in two totally different languages. And this is what led to a huge breakthrough. In the 1940s, two mathematicians, Samuel Eilenberg and Saunders Mac Lane, had a realization. The problem wasn't their specific fields, it was the language they were using to talk about them. What they needed was a meta-language, a way to zoom out and talk about the pure structure of their ideas without getting bogged down in the details of what those ideas were actually made of. And that brand new language they created is category theory. So let's take a look at its most basic parts, the nouns and verbs that let us describe pretty much any system of relationships you can imagine. At its heart, a category is a really simple idea. Just picture a bunch of dots and a bunch of arrows. That's it. The dots are called objects, and the arrows connecting them are called morphisms. It's just a network of relationships. See, the theory doesn't really care what the objects are. It's all about how they connect to one another through these arrows. Now, for this whole system to work, it only needs a few simple rules. First, you've got your objects. Think of them as the nouns. Then you have your morphisms, which are the arrows, or the verbs, that show the action between the nouns. And finally, the most important rule, composition. All this means that if you can follow an arrow from A to B, and then another arrow from B to C, there has to be a single arrow that takes you directly from A to C. It's like a guaranteed shortcut. And of course, this system has to be consistent, and every object needs a little do-nothing arrow that just points back to itself. Okay, I know this all sounds super abstract, so let's make it real with a perfect example, the category that we call set. In this category, the objects are just sets, collections of things, and the arrows between them, they're just functions. And composition is the exact same function composition you probably learned about in school. It's a structure we already know. We're just describing it with this new, incredibly powerful language. So, great. Now we have a way to describe these individual mathematical universes. But how do we get them to talk to each other? For that, we need something called a functor. And you can think of it as a universal translator between these different worlds. To put it really simply, if a morphism is an arrow between objects inside a single category, a functor is an arrow between entire categories. It's the tool that lets us translate the structure of one world into the language of another, and it guarantees that all the relationships are perfectly preserved. It is, quite literally, a morphism for morphisms. And here's pretty much how that works. A functor takes an object from the first category and finds its corresponding object in the second one. But, and this is the crucial part, it also takes the arrows. So an arrow F in the first category becomes the arrow F of F in the second. The entire web of connections is perfectly copied over, just into a new context. Okay, you might be wondering, why are we going through all this abstract gymnastics? What's the point? Well, that brings us to why this all matters so much. It turns out this is an incredibly powerful, unifying idea, with applications that stretch all the way from computer science to fundamental physics. The scope here is just staggering. In computer science, entire programming languages like Haskell are built right on top of it. The types are the objects, functions are the arrows. It gives you a rock-solid guarantee for how your code fits together. And get this. In fundamental physics, it turns out those famous Feynman diagrams that model particle interactions, they're basically just a visual way of doing categorical math. It's even being used to map out the deep structures in music theory. It's everywhere. And this wasn't some happy accident. Eilenberg and MacLean knew exactly what they were building. In their very first paper back in 1945, they wrote that their core ideas were the functor and something called a natural transformation. Now, if a functor is a map between categories, a natural transformation is a map between the functors themselves. It's a way to compare the different translations. They knew right from the start that the real power was in defining these dynamic relationships. But of course, the story doesn't end there. The rabbit hole goes way deeper. So for our last section, let's ask a fun question. What happens when we kick this whole abstraction thing up to another dimension? Okay, let's stretch our minds a bit here. We have objects, right? Like locations. We have morphisms, the arrows, which are like paths between those locations. But what if you could have a transformation between the paths themselves? Imagine you have two different routes from your house to the store. A two-morphism would be like a bridge connecting one of those paths to the other. It's literally an arrow between arrows. This adds a whole new layer and lets us talk about the transformations between processes. So in the end, category theory isn't really about any one field of math. It's about the nature of structure itself. It's a universal grammar for describing relationships. And that leaves us with a pretty big question. Now that we have this language to describe these deep, fundamental patterns, what profound new connections, what entirely new ideas can we finally begin to express?